Good morning, everyone, and welcome to today's lecture. This is lecture number 7, and we are dealing with what we call as Doppler's effect. We have seen what do you mean by Doppler effect. Do you remember what is Doppler effect? Tell me, what is Doppler's effect? We had discussed about the Doppler's effect in the last class. We had seen what is the definition of Doppler's effect. Do we remember this? Please let me know. Or should I go and discuss it again? Tell me, what is Doppler's effect? Are you there, everyone? Yes or no? Whenever we have what? A relative motion between the source and the observer, we have seen that the frequency that we get is different from the original frequency of the sound. This apparent change in frequency, because of relative motion between the source and the observer is known as Doppler's effect. Do we remember this? Yes or no? I'm not getting any response. Are you there in the class, beta? Yes, okay. So that is what we call as Doppler's effect. We had seen two different cases of Doppler's effect in the previous class. In both the cases, the source was moving and the observer was stationary. In case number 1, if you remember, do you remember case number 1? This was the observer, this was the source, and the source was moving towards the observer. In that case, case number 1, the frequency observed by the observer was original frequency multiplied by V upon V minus Vs, where Vs was the velocity of the source. This frequency was greater than the frequency of the original frequency, and the wavelength was smaller than the original wavelength. This was case number 1, where source was moving towards the observer. Do we remember this? Yes or no? No or yes?
Yes, sir.
In case number 2, we had seen again the observer was at rest, but the source was now moving away. This is the case which is there on the screen right now. The observed frequency is now less than the original frequency, whereas the wavelength is more. Today we will start with the next case. And no prizes for guessing what will happen in the next case. Tell me what will happen in the next case, beta. What will happen in the next case? Tell me. In case number 1, we had seen two cases. In both the cases, the source was moving and the observer was stationary. In the coming cases, what will happen? Tell me what will happen. The opposite is going to happen. What do you mean by the opposite going to happen? The source will be at rest. The source of sound would be at rest, but the observer would be in motion. Do we understand this? Yes or no? No or yes?
Yes, sir.
Case number 1, the observer approaches the source. In that case, what will be happening? The observer is coming nearer to the source. What will happen in this case, beta? In this case, the frequency that you will hear will be more than the frequency of the source. Similar case, when the source was moving towards or when the observer is moving towards, the frequency is more and the wavelength is less. Do we understand this? Please raise your hands and let me know. If the source and the observer are moving, any one of them is moving towards the other, the frequency would be more and the wavelength would be less. In this case, the only difference is the formula becomes somewhat different. In case of source moving towards the observer, if I could write the formula here, in case of source moving towards the observer, please remember, do not get confused. The formula was looking like this. Do we remember this? In the denominator, we had V minus Vs. Here, in the numerator, we have V plus V naught, where V naught is the velocity of the source. Do we understand this?
Yes, sir.
If you write the formula for wavelength, the formula for wavelength becomes ulta of the formula of frequency. Formula for frequency is n into V plus V naught divided by V naught. The formula for wavelength becomes lambda into V goes in the numerator, V upon V plus V naught. Do we understand this? Yes or no? I'll give you a minute to note this down. Let us look at the second case then. In the first case, the observer was moving towards the source. What will happen in the second case? Tell me. In the first case, observer was moving towards the source. What will happen in the second case? Tell me.
From the source.
Yes, the observer would be moving away from the source. As you can see, he is moving with a velocity v naught away from the source. In this case, as you can see, the observed frequency will be less than the original frequency, but the wavelength will be more. The formula remains same, but in place of V plus V naught, it now becomes V minus V naught, similar to the formula for wavelength. In this case, it becomes V minus V naught and not V plus V naught. Do we understand this? So the frequency is going to decrease and the wavelength will be increasing. I'll give you a minute to note this down. What would be the general case? Now remember, we have seen the case where the source is moving. We have seen the case where observer is moving. But there is one more thing that is possible. What is that thing that is possible? That they both are
Moving.
That they both are moving. Now, in this case, what will happen? You just put both the formulae together and we can get the answer. This is the first case here. As you can see, both the source and the observer are moving. In case number 1 here, both are moving towards each other. Both are moving towards each other. So you have this formula which becomes the composite formula. Do we understand this? Yes or no? No or yes?
Yes, sir.
The formula for wavelength becomes ulta of this. Yes or no? No or yes? And the frequency will be more and wavelength would be less. Can you write this formula? This formula is nothing, but we take both the cases together. We take the case where source is moving, the frequency is divided by V plus Vs. We take the case where observer is moving towards the source. We multiply it by we multiply it by V minus V naught. and we get the answer. Do we understand? I think this formula is given ulta. I think it is given ulta. There is a problem of a plus and a minus sign. The formula has been written the reverse of what it should be. So there is a printing mistake. So it's better that you correct that printing mistake. Do you understand what is the printing mistake here? Here it should be positive and here it should be negative. Do we understand this?
Yes,
The
sir.
formula has been reversed, right? Yes or no? No, yes.
Yes, sir.
So please correct the formula. Here it should be positive and here it should be negative. Can you correct the formula in the sheet? Yes or no? No, yes.
Yes, sir.
I'll give you a minute to win it. We move on to the next case where both are moving away from each other. And again, the same problem occurs here. The formula is given ulta. Here it should be minus and here it should be plus. Here it should be plus and here should be minus. The frequency will be less than the frequency of the original source. The wavelength will be more than the original wavelength. Do we understand this? Yes or no? No, yes. I'll give you a minute to note it down. I think it was not on the screen. Now it is on the screen. Do we understand this? Again, the formula, there is a mistake of plus or minus. Can you correct it for me? Printing mistake.
Yes, sir.
So in that case, the frequency would be less than the original frequency. Don't worry about that. Just correct the formula. And I will be back. Do you understand this? We have just taken both the cases together. Which both cases together? In which both the source and the observer are moving. First case, source was moving away. Third case, fourth case, observer was moving away. We put all them together, and this is the formula that you get. I'll give you a minute while I will share another sheet with you, which has the correct formulas. This is a misprint. Okay. We move on to the third case, and in third case, what is happening? The source is approaching and the observer is moving away. Do we see this? Yes or no? So this will be the case. The case number two, case number one, source is approaching. Case number four, observer is moving away. We put both the case together and thank God in this case the formula is given correctly. Do we understand this? The formula for frequency and the formula for wavelength are correct here. In case of formula of frequency, V minus VA goes in the denominator and V minus V naught comes in the numerator. Do we understand this?
Yes, sir. Sir, speak loudly.
What happened? You are not able to hear my voice? I think my voice is at the maximum. You can't hear it?
Yes, sir.
Just a minute. Let me check. Is it okay now?
No, sir.
Okay, okay. Just a minute. We start again. And in this case, the source is approaching and the observer is moving away. So this is a combination of case number one where source is approaching and case number four where observer is moving away is divided by V minus Vs and it is multiplied by V minus V naught. Do we understand this? Please take a note. I'll give you a minute. One last case remains. What will be the last case? Tell me. Can you make the case yourself? One last case is remaining. In that last case, what will happen? Tell me. observer will be moving towards and the source will be moving away. Yes or no? No, yes.
Yes, sir.
That is the case right there in front of your screen. V plus V naught is multiplied. Observer is moving towards. V plus Vs is divided. Source is moving away. And this is the formula for frequency and this is the formula for wavelength. Do we understand this? Yes or no?
Yes, sir.
I'll give you a minute to note this down.
Completed, sir.
Okay, we have done all types of cases. But remember, we have not seen the case where the wind might be moving, right? There might be a motion of the medium itself. In our case, where we have sound moving in air, there might be a wind blowing. Now, wind can blow in two directions. It can blow in the direction of the sound or it can blow in the opposite direction. Do we understand this? For example, I am the source. I am producing sound. So the velocity of sound is like this. The wind can flow in the same direction or wind can flow in the opposite direction. Yes or no? No, yes.
Yes, sir.
In that case, something will happen. What will happen is this. When the medium is moving with a velocity Vm in the direction of sound, then the velocity of sound will be written as V plus Vm. If it is moving in the opposite direction, it will be written as V minus Vm. Do we understand this? So in all this formula, V will be replaced by V plus or minus Vm, depending on whether the velocity of medium is in the same direction as the velocity of not source, not observer, but the velocity of sound. Do we understand this?
Yes, sir.
So in all the cases that you have done, you'll have to replace V, which is the velocity of sound, by V plus Vm if sound and medium are moving in the same direction, V minus Vm if the sound and medium are moving in the opposite direction. I'll give you a minute to note this down and understand it correctly. What next? We have seen 4 different cases. We have also seen the cases where wind is moving. Now, one way is to remember all those 4 cases separately. The other way is to remember all the other 4 cases where only one object, when one thing is moving separately. Or what I can do is create a formula. Where if I remember only one formula, I hope everyone is looking at me. I repeat. Either I can remember 4 original formulae and 4 new formulae. In 4 original formulae, one thing was moving, other thing was stationary. In the 4 new formulae, both things were moving. Either we can remember all those 8 formulae or 4 formulae, whatever the way you think, or I can use some brain and make one formula which is applicable everywhere. What is a better option? Remember 4, 8 or remember 1? Tell me. Which is a better option? To remember all those cases or to remember just one? Tell me. Am I audible and am I visible to all of you? So here comes a single formula. If you can remember this, you can use this. This is the formula that I wanted to show you. Frequency n dash or f dash is n into v plus or minus vm plus or minus v naught divided by v plus or minus vm. The last case it is minus or plus. So remember here it is minus plus in the denominator. In the denominator it is minus plus and in the numerator it is plus minus. That is the difference between the numerator and the denominator. Here what we have seen, we have taken the velocity of sound in whatever direction the sound is moving as positive. And then we have made this formula. What will happen is, if the source is moving in the same direction as sound, it will be taken as positive. Source will always move in the direction of sound or not. If the source is moving away from if the source is moving in the opposite direction to the direction of sound, when will that happen? The observer is here, the source is here. So the sound is moving in this direction, but the observer is moving like this. So then observer will be moving in the opposite direction. If a body is moving in the same direction is positive, its velocity is taken as positive. If a body is moving in the opposite direction, its velocity is taken as negative. Then I can use this formula that I have shown you. And once I use this formula, if you can remember this, we can do all the cases. We can do all the cases with this one single formula. Do we understand this? We can do all the cases with this single formula if we understand what? The direction of velocity of sound is taken as positive. The direction of velocity of sound in whatever direction sound is moving is taken as positive. Do we understand this?
Yes, sir.
So please write this formula, and if you can remember it, you can do all the cases with this one single formula, or you have the option of remembering all those formulas, all those formulae together and solve any question. I'll give you a minute to note down this magical formula. So we move on to the next concept, beta, and I have seen direct question coming from this concept. So please remember this. What is happening here is written clearly. Observer crosses a stationary source. So this is my source. It is not moving anywhere. It can be a loudspeaker on a building or some place. The source is not moving, and this is the observer, and he is crossing the source. Do we understand this? The observer is crossing a stationary source. So in first case, it will be moving towards the source, and in the next case, it will be moving away. I mean, the case is only one. Before crossing the source, it will be moving towards the source. After crossing the source, it will be moving away from the source. So the case between before crossing and after crossing, we will hear an apparent change in frequency. Apparent change in frequency. This is the formula. This is the formula when he is moving toward, oops, wrong color. This is the formula when he is moving towards the source. Yes or no? No or yes?
Yes, sir.
I must do it again. This is the formula when he is moving towards the source. Formula number one. This is the formula when he is moving away from the source. Again, a mistake of minus sign. So just make a minus sign. And then frequency number one, n dash, is more than frequency number two, n double dash. The apparent change in frequency will be n dash minus n double dash, and you will have this as the answer for apparent change in frequency. This question has come many times, so please note it down very, very carefully. Do you understand what I am saying here?
Yes, sir.
Please note it down. I'll give you time. Then comes the next case. The observer is stationary. So you are someone who is standing on a road and a car is passing you. Do you understand this? It can move like this, pass you like this, or it can move like this. Whatever happens. In first case, it will be moving towards the observer. In the next case, it will be moving away from the observer. Yes or no? No, yes. Again, you will have an apparent change in frequency. You don't have to understand how this formula is derived. You just have to remember the formula 2 times n Vs by V. In first case, when the observer was moving and the source was stationary, the change in frequency delta n or delta f was 2n V naught by V. These two formulas are exactly similar. In first case, it is V naught by V. In second case, it is Vs by V. Do we understand this? You'll have 1 minute to note it down. Do you understand this? Yes or no?
Sir.
Well, we then come to my favorite part. And my favorite part is the question and answer part. And this is the first question that we are going to deal, which is question number 1 of your sheet. Doppler's effect will be more effectively observed when the observer. When do we have the most effective Doppler effects? Option A, B, C, D. In option A, it is moving along the line. In option B, it is moving perpendicular to the line. In option C, it is moving in any direction. And option D is none of the above. Can I have your answers, please? Which
Yes,
is the most effective position or motion in which you will have the maximum Doppler effect? And the answer is definitely?
A. A.
And the answer is definitely A. It must be moving. Oops. Things happen when they should not happen. It must be moving in the direction, in the line joining the observer and the source. Do we understand this? Yes or no? No or yes? Because they are moving perpendicular,
Yes,
there is no Doppler effect. This is question number 8 now. Next one. A source of frequency n is moving with a uniform velocity v towards a stationary observer. Remember, observer is stationary. If the velocity of sound is capital V, remember, Just don't get confused. Velocity of sound is capital V and the velocity of source is small v. What will be the frequency? And what is your answer, bacha? What is the answer that you get, that you have, that you know?
A, sir.
And the answer is
A.
A. How do you get A? V minus V, a source of sound. Source is moving with a uniform velocity V towards a stationary observer. That means this is case number 1. Yes or no? No or yes?
Yes, sir.
And the option is not A. In option A, we have small v. Small v here is the velocity of source. Capital V is the velocity of sound. Do you remember the original formula? Yes or no? No or yes?
Yes, sir.
So what should be the answer, bacha?
C.
Answer should be C. Why did you say A? Are you looking from the answer key? Sometimes the answer key may also be wrong. Yes or no? No or yes?
Yes, sir.
So don't give answer from the answer key. Anyone can do that. Okay? I hope you will not repeat the same mistake again. Okay? So remember, it is the velocity of sound in the numerator and V minus Vs in the denominator. Don't make mistake, beta. Next one is this one. Doppler effect is not applicable to where? Everyone knows the answer for this one at least. I am fully confident that you are aware. I can't see your fingers because your fingers are getting lost in, yes. 3, shockwave, 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 shockwave. We had discussed this case and you know this. That is the good stuff. Then we have this one and let us see, let us hope that we are not going to do mistake in this one. And this is question number 9 coming to you. If an observer is moving with uniform velocity v towards a stationary source of frequency n, velocity of sound is v, then the apparent change in frequency. Oh, in this sheet there are a lot of. Then the apparent change in frequency. How much is the apparent change in frequency? We have seen the formula. Yes or no? No or yes? Obviously, none of these formulas are matching. It is 2 times v into V naught divided by capital V. Yes or no? No, yes.
Yes, sir.
So the answer is B, but the only thing is 2 is not mentioned here, so you must mention 2. Yes or no? No, yes. So I guess there are a lot of mistakes in this sheet. Printing mistakes, I must say. Typing mistakes, I must say. Anyways, I'm telling you the correct answer. This is the next one. A source of sound crosses a stationary observer. Source is moving. Observer is not. Let me see. Please do not refer to the answer in the answer because the option may be correct. The option may also be wrong. Source is moving towards an stationary observer, which is the ratio of apparent frequencies heard by observer before and after. Before and after they are asking. Before and after they are asking. What will be the ratio? Before and after. And what is the answer? To find the ratio of the frequencies before crossing and after crossing. May I have your answers, please? The ratio of apparent frequencies heard by the observer before and after. And the answer is 1. Yes, that is correct. And thank God all the options are correct. And the answer is also given correct. So we must thank everyone who has helped in making this sheet because now the answer is correct. This is the next one that comes to you. This is the next one. Let's see who can give me the answer for this one. A straightforward question with a straightforward answer. And I'm waiting for it. Which of the following properties of the wave is proved by the Doppler's effect? Wow. Longitudinal, transverse and longitudinal. Neither longitudinal nor transverse. It does not prove anything. Does not prove anything. Wow. Great result. It does not prove anything. Which one is the correct option? Which effect or which nature is it proving?
D.
Neither. See, Doppler effect is visible in is observable in sound waves. Sound waves are longitudinal waves, but you can also observe it in light waves, EM waves, which are treated as transverse waves. So it happens in both transverse wave as well as longitudinal waves, and therefore it does not prove anything. Do we understand this? Yes or no? No, yes.
Yes, sir.
Yes, sir. Then, sir, next question, sir, coming to you on your screen, sir. And I hope that the answer and the option are correct, sir. So tell me the answer, sir. If a source of frequency n crosses a stationary observer with a uniform velocity v, and if the velocity of sound, capital V, is much larger compared to small v, then the change in the frequency due to Doppler effect would be, and I'm waiting for your answers. And there's only one correct answer here. I must tell you that. What is that one? I hope you are not looking at the answer key and giving me the answer, because even my kid, who is right now in second standard, he can tell me the answer that way. He knows how to read A, B, C, D. He also knows table up till 20, which probably you would not know. Anyways, yes, tell me. Are?
A.
A for apple. Yes, A for apple is the correct answer here. A for apple, correct. Let me move on to the next one. And A for apple, B for ball, C for cat, D for dog. Question number 13. Which one? Apple, ball, cat, dog. 1, 2, 3, 4. Apple, ball, cat, doll, dog, whatever. Can I have the answer?
Dog.
Yes, dog. Dog are very nice animal. I love them. I always had a desire to have one of these at my home, but my desires were unfulfilled. My mom and dad won't allow me to keep them. I used to go to nearby places where they had the small puppies, and I used to play with them. Once I got one puppy without telling my mom and kept it in my room. And then in the night, she or he started crying, and there was a lot of fuss in my room, in my house, because of that. That was the last time I had a puppy in my house. Now I can keep one. My son always asks me to keep one, but now I don't allow him to do that, because it's difficult to take care of these animals. They require a lot of attention. And then when you have these animals in your house, no one comes into your house because everyone is scared. So that is the next reason. And third reason is that they will move everywhere in the house, and all sorts of, they shed their hair, and that will create a lot of gandgi in the house. So if you have a farmhouse, you can always keep all sorts of pets. Otherwise, we restrain ourselves from this pet business. So that finishes our discussion for Doppler's effect in sound. A very small topic that remains is Doppler's effect in light, and we are going to go ahead with the same one. Doppler's effect in light. The velocity of light in free space is independent of the motion of the source or the observer. That is the main point here. The velocity of sound is not independent. It also depends on the medium itself. And it is a universal constant, the velocity of light. Thus, the Doppler's effect in light depends only upon the relative motion of the light source and observer. It does not depend on who is moving. Do we understand it?
Yes, sir.
So you will observe Doppler's effect in light, no matter the source is moving towards the observer or the observer is moving towards the source, doesn't matter. What matters is whether the distance is decreasing or whether the distance is increasing. Do we understand this?
Yes, sir.
Pakka.
Pakka.
Okay, I'll give you a minute to note this down. Well, so as I say, that the Doppler effect in light does not depend on who is moving. It only depends on the fact whether the distance is increasing or whether the distance is decreasing. So two cases can happen, and you must remember the two cases. And what are the two cases that can happen? The light source, the star, is moving away from the earth. Now, when the star is moving away from the earth, what will happen is your frequency that we see will decrease or the wavelength that we see will increase. Remember, that is what you need to remember. The formula is not in your course, but what you got to remember is what is going to happen. What is going to happen, bacha, is the frequency is going to decrease or the wavelength is going to increase. Do we understand this? Yes or no? No or yes?
Yes, sir.
Now, if the wavelength increases, the line will shift towards the red end, and we know it as the red shift. Did I tell you in the very beginning that sometimes you see star appearing red and sometimes you see the star appearing violet? Yes or no? No, yes. When the star appears red, it is actually moving away from us, or we are probably moving away from that star. Do we understand this? Yes or no? No, yes.
Yes, sir.
I'll give you a minute to note it down. Redshift. Let's move ahead and see what will happen if the light source or the star is moving towards us or we are moving towards the star. The frequency, oops, the frequency will be more or the wavelength would be less. The wavelength will be decreasing. The spectral line will be displaced towards violet and we call it the violet shift. These are the two things that you must remember about the Doppler effect of light. Redshift and violet shift. Redshift means frequency is less, wavelength is more, the star is moving away. Violet shift means frequency is more, wavelength is less, it is shifting towards violet. Do we understand this? I'll give you a minute to note this down. Let's move ahead and see point-wise what are the difference between Doppler effect in sound and Doppler effect in light. One of these points will be coming in your exam. Doppler effect in sound depends on whether the source is moving towards the observer or the observer is moving towards the source, where the source is moving away or the observer is moving away. This does not depend on who is moving. It only depends on whether the distance is decreasing or whether the distance is increasing. Do we understand this better? Doppler effect in light does not depend on who is moving. It only depends on whether the distance is decreasing or whether the distance is increasing. Do you see me? Do you hear me? Am I there? Okay. The velocity of the medium affects the apparent frequency. The velocity of the medium or no medium, light is going to travel in vacuum. The velocity of the medium has no effect here. Do we understand this? A minute to note this down. Very important point because one of these points will be coming there. Okay, the next 2 points are not of so much importance because they will not be asked, but just to note them down, ordinary laws of vector addition is used in sound. They are applicable, but speed of light is known as relativistic, and relativistic mechanics के laws are applicable here, which you don't know. Transfer Doppler effect, not in your course, is not applicable here. Transfer Doppler effect is applicable here. Again, these things are not in your course, so there is no point that you should remember this. Do we understand this? Okay, so just note them down. Okay, then here are 2 or 3 questions that we should discuss so that we wind up this topic. These are the type of questions that you can expect in the examination. All Doppler's effect in light differs from Doppler effect in sound because A, B, C, D. Just now told you the answer. Which one is the correct option? Tell me, bacha. A, B, C, D. Apple, ball, cat, doll. So velocity addition is not applicable just now. I told you this. Well done to remember this. These are the ways you knew. What happens is, if you understand something and you remember it, you would be doing good. Now comes the next one. The velocity of light emitted by a source S, an observer by an observer O, which is at rest with respect to SC. The observer starts to move towards S with a velocity v. What is the velocity of light as seen by the observer? A very basic question. And the answer is C minus V, C plus V, C under root of something. Which is the correct answer, bacha? And the answer is C. Speed of light does not depend on whether you are moving or the light is moving. Speed of light is same. Do we understand this? Yes or no? No, yes.
Yes, sir.
Yes, remember this. And remember this formula, 2 formulae. And I'm showing you the next one. Due to relative motion between a star and Earth, the following relation is obtained between the wavelength of light from the star and Doppler displacement. Delta V. Vs is the velocity of the star, how fast the star is moving. Which formula is correct? There is only one formula which is correct. Remember that C is always in the denominator and the speed of star or speed of Earth or whatever is always in the numerator. Do we understand this? Delta lambda by lambda is Vs by C. Vs, velocity of star, will always be in the numerator and the speed of light will always be in the denominator. Therefore, the apparent shift will be very, very small because speed of light is 3 into 10 raised to the power 8 meter per second. Do we understand this? Well, then that is the formula for apparent shift. What we have seen today is we have finished Doppler effect in sound. We have seen the various cases of Doppler's effect in sound. We have seen that Doppler's effect depends on whether the source is moving towards the observer, whether the observer is moving towards the source, whether they are both moving towards each other or away, or one moving towards and the other moving away. Doppler effect in light does not depend on these factors because it only depends on whether the distance is decreasing or distance is increasing. Speed of light in all frames of reference should always remain fixed. It cannot change. Cannot change the speed of light. Remember that. Well, on that note, we finished Doppler's effect. We are done with all possible things. I'll give you 5 minutes to go through the entire Doppler effect and we'll come back with the next lecture. Get your notes. The next lecture is EM wave. Since we are talking about light, Doppler effect of light, it's good that we shift to EM waves, electromagnetic waves. That would be the next lecture. Take care and steady, and I'll give you time. Take care.